this session. So today we're going to cover vector spaces. Let's begin. So first of all, let's see what are vector spaces. Before defining vector spaces, I think we should first define the idea of a field. So currently, you'll be considering for the scope of this lecture, you'll be considering fields, which are either real or complex. So we won't be going too much into the uh, formal definition of fields as we have in abstract algebra and all this stuff. So basically, for the purpose of this course, we define field as a set of scalars. With addition and multiplication defined on the set. So field actually should satisfy a few properties. We can take this as given for a particular field. First of all, it should be closed under addition and multiplication. What it means is if we have an operation which is an addition on a particular field, after the operation, we'd end up getting a scalar which is in the same field. So it's closed under addition, closed under multiplication. So if you're, for example, if you have a set of real numbers, we're taking two numbers like A belongs to R and B belongs to R, then A plus B belongs to R or C. This is what we have. Similarly, A dot B also belong to R. This is what is meant by it is closed under addition and multiplication. Next property it has satisfies both addition and multiplication are associative and commutative. What does that mean? How do we formally define associative? In the sense, if we have A, B belongs to a particular field, then let's say A B, C belong to a particular field, then A plus B plus C is same as A plus B plus C. Similarly, A dot B dot C is same as A dot B dot C. This is the associative property. Then we have the commutative property, which basically says A plus B is same as B plus A, and A dot B is same as B dot A. These are the commutative properties. Commutes. Okay, so another important property is their excess an identity element. Identity element in terms of both addition and multiplication. So a plus 0 is a. This was the additive identity. Similarly, a dot 1 is equal to a, which is the multiplicative identity. Okay. Then there exists an element. So for every element, there exists an additive inverse. What does that mean? A plus minus a is equal to 0. So what is 0? 0 is already, we have defined it as the additive identity. And what does that mean? Here, minus a is the additive inverse. Also, for every element except additive identity 0, there exists a multiplicative inverse. Or if rewrite it, let the more formal way of writing it is let a belong to f, then there exists a b which belongs to f such that a dot b is equal to 1. And the last property is multiplication is distributive over addition. What does this mean? We have a b belong to a field. We have two operations, a dot. Okay, we should have a b c belonging to field c. Yeah, a dot b. This multiplication is actually can be distributed over this addition. The same as a dot b plus a dot c. So for the requirement of this course, for the current discussion, we can restrict ourselves to the this definition of a field. Let's quickly revise what the properties of a field are. We can kind of like an axiomatic definition. A set of scalars with plus and minus defined on the set. It's closed under addition and multiplication. They're associative and commutative. We've seen what this is. There exists an identity element. There exists an identity additive inverse, multiplicative inverse, and multiplication is distributive over addition. Okay, so once we have actually formally defined what is a field, then we can actually go to the idea of vector fields. So the vector spaces. So vector space. Let's say let us call script field as vector space. Okay, over field F. So whenever we are actually discussing about vector spaces, we also define we have to define it over a particular field. Okay, so vector fields has to satisfy the first condition is if x comma y belong to a particular vector space, implies x plus y also belongs to the vector space, which is closed under additional. Second is if x belongs to V and V belongs to field F, then Cx belongs to vector space V. There's also an implication. Yes. 0 belongs to this part of vector space Y because for E is equal to 0, C should be equal to 0. 0 is actually the vector. This is a scalar and this is a vector. Okay, this is an implication. So if we have a field over which we have defined addition and multiplication, and if it satisfies all these properties, all these axioms, then this is how we define a vector space if it satisfies these two properties. What are these properties? It's closed under addition, it's closed under scalar multiplication. So if these two properties are satisfied, we can call it a vector space. Yeah. Yeah. This is the basic idea of vector spaces. Let's stop the discussion of vector spaces now.